Hey guys, welcome back to General Chemistry. For my course, this will be the start of Chapter 2. The first thing we're going to talk about in Chapter 2 is early ideas in atomic theory. So I'm not going to be a stickler on names and dates and all that kind of stuff, but I think it's important to know where we came from in order to know where we're going and build a solid foundation moving forward. So we're going to first talk about early ideas in atomic theory. So a little bit of history. The first to theorize about atoms was the Greek philosophers back in 400 BC. So during the time of Aristotle, Plato, we've got Democritus, who was the first to theorize that matter is made up of atom or atomos, uncuttable particles. Unfortunately, he was not the most popular of the philosophers. Aristotle and Plato were a bit more popular, so the ideas that they had about matter prevailed. So they said that matter is a combination of earth and water and air and fire. And because of their popularity and because there was no way to test these theories, they prevailed. And their ideas prevailed for a long time, even though Democritus was correct. So it wasn't until the 16th century that the modern scientific approach started to emerge. So there was an emphasis on observation, data collection, and this led to, by the 1800s, convincing evidence to support this atomic theory, to support the fact that Democritus was correct, and that matter is made up of these tiny particles called atoms. So this is where we have our first introduction to the Daltons atomic theory. Okay. So the modern atomic theory and its laws. So a lot of times textbook goes into a big conversation about all of these laws. I don't at this point, just because you don't have the knowledge foundations to build on here. You don't have the knowledge to really understand what these laws mean. So I'm showing you that during this time we came the law of conservation of mass, law of definite properties, and law of multiple proportions. Okay. So this original atomic theory that started to come out in this 1800s. So 5 postulates can be summarized in. Matter is composed of tiny, exceedingly particles called atoms, and the smallest unit of a particular element is the atom. So anything smaller than that, and it doesn't retain its chemical properties. An element consists of only one type of atom that has a mass that is characteristic of that element, and this is the same for all of the atoms of that element. So while this atomic theory was good, certainly given the time, this is one of the areas that as we started to learn more, turns out it wasn't this way. But this was part of the original atomic theory. Atoms from one element differ in properties from atoms of all other elements. So all this is saying is that all aluminum atoms behave like aluminum atoms. They're metal, they're shiny, they conduct electricity, and aluminum atoms would be different than any other atom, so it'd be different than a carbon atom. So that's what this is saying is one element has all the same properties, and those properties are different than other elements. A compound consists of 2 or more elements combined in whole number ratios. So if we want to take these elements and we want to connect them together, that's when we have a compound. And we're going to have whole number ratios. So you're not going to have 2.5 carbons attached to 1.6 oxygens. They're going to be whole numbers, 1 to 2, 2 to 2, that sort of thing. And then lastly, atoms are neither created nor destroyed during chemical changes. So we're just simply rearranging the way that atoms are all put together. We're not pulling in and poof, there's a new atom, or oh, where'd that atom go? So they're neither created nor destroyed during these chemical changes. So while this was a very good start, a very good postulate, It wasn't entirely correct. And there's also a lot of things that it didn't answer. So there's more to the story. Turns out atoms aren't the smallest particle. We have these things called subatomic particles. So that's what this next section is about. So around the end of the 19th century, J.J. Thompson was doing some work with a cathode ray tube, and he was the first that discovered these subatomic particles. So what a cathode ray tube is the following. So cathode ray tube, you've got some sort of voltage source, and then you've got an anode and a cathode, or a positive and negative. So this is just creating some sort of separation in voltage. So we're going to take our ray, we're going to shoot it through that separation of voltage, and then out the other side is going to come a beam of something. I'm trying to figure out what that beam is. The cathode ray tubes were kind of the hot ticket during this time because it was like a bright glowing green beam, and that was really cool for scientists at that time. So these were kind of the hot ticket, the one thing that was being studied quite often. So inside of this sealed glass tube, we've created this glowing green ray. And then scientists started to see, well, can we move that ray? Can we mess with it? So just the plain, simple experiment, this ray would come out. It would move in a straight line, and it would hit a detector over here, right out in front of where that ray came out. So the detector was hit. Then scientists started to introduce electric and magnetic fields to see if that ray would start moving. And what they found is it did start moving. So they would introduce some sort of electric field or introduce some sort of magnetic field. And what they found is that ray would be attracted towards like a positive charge, and it would be repelled by a negative charge. So there must be something inside of that ray that is causing it to move. If it's repelled by a negative charge, if it's attracted to a positive charge, there must be some particles in there that are in fact charged. So as it turns out, atoms, which they thought were neutral, now contain particles that are charged. What particles could be in there? The next experiment that we're going to talk about is the Millikin Oil Drop experiment. So once scientists discovered these particles and the fact that they were charged, the next thing that we wanted to determine was, what is that charge? And what we discovered with the cathode ray tube and then the Millikin drop is we discovered electrons. We discovered that these particles had negative charges. And as it turns out, the Millikin oil drop could give us exactly what that negative charge was, like how many volts it was, which is pretty mind-blowing that they were able to do this. So long story short, with this Millikin oil drop experiment, they had an electrically charged oil droplets. They were able to so they allowed them to drip down, and they were able to slow down how fast they dripped. And they were even able to kind of stall it inside that system. So by changing the electric field, they were able to slow those drops down to kind of stall them, and that determined exactly what the electric charge was for those particles. So we know they're negatively charged, and now we know exactly what the charge is. Okay. So where are we? Like any good experiment, we discover or we uncover this knowledge, this information, but then it always raises more questions than it probably answered. So here we are with the atom circa 1900. We know atoms are neutral. So inherently, I have an atom in my hand. It is a neutral particle. So if atoms are made up of electrons, this negatively charged particle that we discovered, what else is there to balance out the charge? So if we know there's a negatively charged particle in there, what is positive in there that's balancing it out to make it wholly neutral. And then if we determine or discover what is in there that's positive to balance it out, well, how is everything arranged? What are those positive particles at? Where are they located? What do they look like? Or is it just a region that's positive? I don't really know. So the first model that was proposed is something called the plum pudding model. So I don't know how many of you are familiar with plum pudding, but apparently plum pudding is like a crust on the outside, and inside is like goo or breading with like raisins or something scattered throughout. So plum pudding model. Probably not terribly familiar with plum pudding. So I like to call it the blueberry muffin model. So here's our blueberry muffin model. So what they proposed is that we have this sphere of positivity. So if we think about a blueberry muffin, the sphere of positivity would be the breading on the outside and on the inside. So the breading is that sphere of positivity. And then inside is scattered throughout that sphere of positivity, we've got electrons or blueberries. Okay. So this was the model that they proposed at the time. So we knew there's electrons, we knew the atoms are neutral, and we think this is how it's all put together. Is that, in fact, the model of an atom that we discover today? Or that we learn about today? No, it's not. So how did we get from the blueberry muffin model to the atom that we know today? I'll let you know in the next video. We'll talk about the gold foil experiment. Hope you guys found this helpful.